Welcome back to the 2025 Everybody Codes contest. So we're back from the weekend, and today we're looking at quest number 6. So now that we have these swords for the knights, we now need to train the knights. And so it looks like there are 3 different disciplines for the knights, and they need to be mentored according to those disciplines. So a capital letter indicates an expert in some discipline, so capital A is an expert in sword fighting. And then the lowercase letters indicate knights that are novices and need to be trained. So for example, lowercase c needs to be trained in magic. And so we're going to determine the total number of possible mentor/novice pairings. So looking at the first problem, this string basically tells us where all of the knights' tents are positioned. So this means that the first tent has a mentor in sword fighting, the second tent has a mentor in archery, the third has a novice in sword fighting, and so on and so forth. For part 1, we're just looking at the sword fighting category, and so we see that if we remove all of the other tents because they're irrelevant, this gives us all of the sword fighters. So there are 2 mentors and 3 novices. And we see here that there's a rule that the mentor has to appear earlier in the list than the novice. So looking at this, that means that there are 5 possible pairs, and so we want to determine the total number of pairs in the sword fighting category. So we can take the input as just one line, and if we want, we can filter out the capital and lowercase a's. However, it isn't really necessary to do so because we're looking for the number of capital A's before lowercase a's, and whether or not there are characters in the middle doesn't actually affect it. It will be slightly more efficient to do the filtering, but it really does not matter, and given that it's a contest where you're trying to write your code as quickly as possible, optimizations aren't worth making unless the amount of time it saves in runtime is greater than the amount of time it takes to write it that way. So what we can do is we basically just want to iterate through the string with 2 pointers. We want 2 indexes I and j, such that I is always to the left of j, which lets us check if index I points to a capital A and index j points to a lowercase a, then we have a pair that is valid. In order to do that, we can start j at I plus 1 and iterate to the end of the line. So this says for each left index from 0 up to the end, and for each right index starting strictly to the right of the left index and until the end of the line, we check something to do with line I and line j. And what we're checking here is very simple. If the left index points to a capital A and the right index points to a lowercase a, then we want to increase our total by 1. And so that gives us a relatively straightforward part 1, like so. Part 2 isn't too surprising. We're just no longer checking only the sword fighting category, we're now checking all 3 categories. And it's the exact same process as before. So again, you could partition the string into the A's, the B's, and the C's if you want. It'll technically be more efficient this way, but we don't really care. Not too much needs to be changed here. Now we're looking to see if the left index is uppercase and the right index is lowercase, and that they match with each other such that they're in the same category. So we can check that the left index is equal to the right index uppercase. And then we also need to check that the left index is uppercase and the right index is lowercase. This here already checks the first of those 2 conditions, because if line I equals line j uppercase, then that necessarily means that line I is itself uppercase. And then we just need to make sure that line j is itself lowercase, because we're not looking for pairings between 2 mentors. So we can do in ABC to check that line j is lowercase. You can also do a variety of other things like line j dot is lower, or line j is less than or equal to z, or stuff like that. I think is lower probably makes more sense in this context, so let's go with that. And that gives us the answer for part 2. Also fairly straightforward, like so. Finally, part 3 is an interesting continuation. I've seen this sort of stuff a lot in Advent of Code. Essentially, we're doing the same thing as earlier, except now we're just making the input really large, basically. So this time we are changing the approach slightly. Rather than looking at only mentors before it in the list, we are repeating our segment 1,000 times and using a new method where the novices can only be mentored by knights that are within 1,000 tenths of them. Now that can be either to the left or to the right. So for example, in this instance where we are temporarily setting the distance limit to 10 and only repeating the pattern once, we can see that these are our pairings. So for this novice in sword fighting, they have 4 mentors that are within range. These 2 are too far, and this one is also too far. This novice in archery has these 6 mentors in range, and this one is out of range, and so on and so forth. And we're just getting the sum of pairings at the end as well. So it actually turns out that you don't really need to do too much optimization here, interestingly enough. So if we just copy over from here, instead of looping from the next index to the right of I, what we can do is, since I is supposed to be the mentor and j is supposed to be the novice, we are going to need to switch the indexes around here. So I'll do that in a bit, but what we can do is, instead of actually iterating through j, we can use a string slice. And so the left index is going to be the index itself minus our range, which is, let's do 10 for now just to do the example case. And the right index is I plus 10. And so the string that is relevant, the local string basically, so for this A, the local string would be this block here, or whatever it is. That's the string in which we're going to search for mentors. So we can do string equals line from left index up to right index inclusively, and then we can increase the total by the count. And so I found that this is faster than iterating manually, and I'm not exactly certain why. I'm assuming it has something to do with like under the hood optimizations within the C++ probably, or C, I forget which one Python uses. I imagine it probably has something to do with this slice not actually creating a new string and just using a pointer, unless you try to modify something in the string. And .count might be a native function or something along those lines. I'm not too sure. And then the last thing we need to check is that, first of all, we need to put in what we're actually counting. So for the character is line at index I. If the character is uppercase, then we skip it. And then if it's a lowercase letter, we look in the range for characters equal to its mentor type. So I'm certain I've made some one-off errors here, so this is probably, oh, maybe it will work the first time. Okay, let's try repeating twice. We get 72, okay, cool. And so if we now repeat the pattern 1,000 times and change this range up to 1,000, we can see that, unexpectedly, this is not giving us the correct answer. And right. The reason for that is because I forgot to clamp the indexes. The left index can't be any less than 0. Because if it is, then I think it tries to go out of, like, wrap around to the other side. And the right index can't be any greater than the length of the line. And I think since... No, I think this works fine. Okay, and so that gives us the correct answer. Now, for our actual input, because the input string itself is so long, this will take a while, but it will actually complete. And okay, I think I'm running into the same issue again, where the input is so long that it's being cut off by my terminal. So if I try doing it like that, we will see that this will eventually complete. And it takes under a minute from the last time I tried. The exact timing might change, but we can discuss a more optimal way now as we let this run, which is we can notice a pattern as we repeat the string. So essentially, because we're only looking at numbers within a certain range, that means that the number of mentors in range of each novice also forms a loop. And if I open up the board here, we can see that we have some chunk of 2001 characters. And then since we're repeating our entire string several times, the same A will show up here. And even if this range bleeds over into the next string to the left or to the next string or to the right, it is going to functionally be the same as the next one after it. Which means that each time we add a new segment, the total count of the pairings will go up by the same value each time. Basically, the first string will have a different value because there will be missing values to the left. But then each time we add in a new string, we'll be increasing the count by the same amount. Which means that if we get the sum for when we repeat the line just once, and then we get the count for when the line repeats twice, we can then just solve the linear equation to determine what it is at any arbitrary number of repetitions. So we see that this, in the time it took me to explain that, it already did get the correct solution. But if we want one that's more optimal, what we can do here is put this into a function. And then we can keep track of what happens when we repeat the line once, and what happens, or 0 times, I guess, and what happens when we have the line printed twice. And so if we look at those two numbers, then basically what we now have is a function of the number of repetitions r, and we know that f of 1 equals x and f of 2 equals y. And we established that the function increases linearly, meaning that if we take this difference, delta, then f of 3 is just equal to f of 2 plus delta. F of 4 is equal to f of 3 plus delta. And so eventually we see that f of 1000 is just f of 1 plus delta repeated 999 times. And so given the values 1 and 2, delta is equal to 2 minus 1, of course. And so our final value that we're trying to get at 1000 repetitions is 1 plus 2 minus 1 times 999. Which we can see instantly gives us the correct value. You can simplify the math, or not really simplify it. You can reduce the math a bit like this if you really want, but it honestly doesn't make a difference to the length, and it's a bit less quick. So I think this is the preferred method. But yeah, and so that gives us our solution for part 3. Interesting problem. Doesn't require you to see the linear function optimization. You can just brute force it. But interesting problem nonetheless, and I like today's problem. The first part was relatively trivial. Second part was honestly like the exact same as part 1, but the third part definitely did take me a second. Kind of sucks that it is actually still within range to just brute force. I lost a bit of time doing some unnecessary optimizations. I did a rolling window optimization, which I guess I can go over in a bit, but that honestly costs me time and resulted in me not getting an optimal time because I spent longer optimizing than I saved with the optimization. The rolling window approach is something that would potentially be necessary if there weren't repetition patterns that we could take advantage of. So the way a rolling window works is essentially, recall that each time we are looking at a specific window in the string, and then when we go to the next character, we're looking at a window that's only one place over. And so the difference between the number of mentors in these two strings is going to be at most removing this mentor and adding in this mentor. Which means that we don't have to recount the entire string each time. We can instead keep track of the string that we are tracking, but also keep a map of the number of mentors of each type within this string. And then each time we move the window over to the right, we add this one to the count and subtract this one from the count. And so basically, instead of looking at the getting a new slice of the string each time, we're going to start with a slice and then move the slice over by 1 each time. So we can start with a slice, which will be the first 1001 values. And the reason for that is because the first item in the string, where this is the start of the string, is going to be this character and the 1000 within its range. And so we'll initialize a count map. And then we can do for ch in slice. If ch is upper, then count ch plus equals 1. Okay. And now we're still going to iterate through the index of the line. And we're still going to get the character in that line. But now we're not going to skip the uppercase letters because we still need to move our slice. And we can do if c dot is lower. We can simply add the known number of mentors of that same type to the total. And then we want to move the slice over. So in order to move, sorry, let me make this actually a slice. In order to move the slice over, we know that we first need to add the next character. So if I plus 1001 is, or I guess if I plus 1000 is still in range, then we'll add it to the slice. And then, sorry, let me make sure I'm not making one-off errors. I believe it should be 1001, yes, because this is the next index, so I is already we need to treat I as though it's increased by 1 here. So if I less than 1001 is less than the length, then we add it to the slice. And if it's uppercase, I guess we can make this simpler by putting next equals line I plus 1001. We add it to the slice. If it's uppercase, then we add it to the count. And then we also need to remove the first item in the slice as we move the window over, but not the first 1000 times, because remember that we initially start with nothing on the left of our window, and then each time we add a new value, we don't actually need to start removing values until we've filled out the full 1000 to the left. And at that point, we'll have to start removing values from the left. So if I is greater than or equal to 1000, then we'll remove the first element of slice. So if slice 0 is uppercase, then we'll need to remove it from the count, and then we will chop off the first element. So this will probably have some... Oh. No, I guess I actually did get it right the first time. That's always surprising to me, because I almost always make one-off errors with what numbers these should be and whether they need to be adjusted by adding 1 or not. So yeah, that is the approach I ultimately went with for this problem, was both having the rolling window approach to save on operations and using the linear function optimization. Turns out that you only need to use this one. I'm curious if you can actually just only use the sliding window one. I imagine you can't, because you're still iterating through okay. I guess either one of those alone would have been fine. And like I said, I'm somewhat disappointed with the fact that you actually don't need either of them if you just use Python's string slicing, which is apparently very fast along with the count function. It's fast enough that you can run it a million times and it's still somehow fast enough. But I do like the potential in this problem for all the optimizations. So I think I'll stick with uploading the rolling window approach to the GitHub repository. Again, that's in the description if you want to check it out, and all of the previous solutions Python files. But you do not need to see this linear optimization, and you also do not need to know the rolling window approach if you just use the same old method from part 1 and part 2, but modified to get the ranges correct. Then using the linear optimization is more than fast enough. So that's all for today's problem. Thank you for watching, and I'll see you tomorrow.